Okay. All right. Let's get started, right? Okay. Well, welcome everyone to January's DataWorks MD meetup. I hope everyone had a safe and happy holiday and everyone's doing well and ready to kick off the season with some interesting talks. Very excited about today's speaker, Tina Coleman from ClearEdge, discussing malware detection with machine learning. With everything going on in the world, with the solar winds and always cybersecurity concerns, I think it's very relevant. Tina's been doing a lot of work in this area with IRAD, and I had sent out some resources. There's a book there's some more information. I can post that in the chat afterwards. But before we get started, I'd like to thank our sponsors and then just go over some logistics. So Variant Technologies is a small business focused on defense contracting and federal government contracting. They do a lot of software engineering, system engineering, and data science work. So if you're interested in learning more about those opportunities, you can reach out directly to them, or you can always get in contact with me. And then ClearEdge is a partner, so Tina's from there, but they're doing amazing stuff, as you're going to see with the work they're doing with the malware data science. So they have a thriving IRAD group. They do a lot of work with analytics, data science for various customers. Just a really great company, and they've been very supportive of the group. We previously had a talk at their venue featuring analytic discussions from Cyber Command. So if you're interested in learning more about them, you can reach out to myself or Tina or the information there. Aries Ventures is my company. I usually don't focus too much on this one. We're very small, but if you're just interested in learning what we have in mind, what we're trying to do, go ahead and reach out, and I can tell you what I know. I love meeting new folks and sharing and seeing if there's a fit, and if not, still trying to help folks. Just feel free to reach out. So we're working on the schedule for the next couple months. We do have next month posted what's going to be machine learning design patterns. And then we have some other ones in the discussions like data science for national defense, maybe data waves, some other interesting talks coming. We do have a monthly newsletter that goes out. If you're interested in that, you can always sign up from the website. And if you have any suggestions or have any interest in working on a conference or speaking at a conference or sponsorship, please reach out. I'm always willing to work with people. We are doing some interesting things. Like there's a group of people in the meetup that are working with the Baltimore City on some data related projects. If you're interested in that, reach out. So with that, I'm going to get ready to hand it over to Tina. Tina is the technical director for ClearEdge. She is accountable for furthering the company's depth in cybersecurity. And we had talked a little before this. She does a lot with the IRAD. And as you'll see in this talk, she's been spending a lot of time working in the area of malware with data science. So with that, I'm about to hand it over. Final thing is for the questions, I will be monitoring both the YouTube and the Zoom channels. I'll gather all the questions. Tina asked that they're asked at the end. So I'll gather them and we'll go from there. But I'm hoping to see a good conversation and a great presentation. And with that, I'm going to mute myself and hand it to you, Tina. You can share your screen. It's all you.
All right. Very good.
Oh, one last thing. I would say the YouTube, there is a delay. So if you ask your question and you don't think it's going to get answered or asked, just give it a minute because then it'll catch up and I'll ask the question. All right. All you, Tina.
Very good. All right. Okay, let me see. What do we got here? Okay. Let me go back just a moment. All right, so our topic today is malware detection enabled by machine learning. I am peeking at the chat. If somebody believes that they can't hear me, they're seeing the voice monitor go up and down, let me know. But otherwise, as Jason suggested, what I'd like to do is work through our material. It includes a demo. Hopefully, I've pre-thought of the questions you're likely to ask, and if I don't answer them immediately at the point where you think where it came to mind, it'll catch up later in the deck. But that'll give us a chance to have a conversation at the end. All right. So my name is Tina Coleman. As Jason mentioned, I'm a technical director and what's called a principal solutions architect here at ClearEdge. I'm also the director of what's called our WIT, or Women in Technology program. My personal background is mostly as a software engineer. Careers spanned everything from mobile development to writing web applications that dealt with radio frequency analysis to working on the latest thread has been a lot related to how do we deal with things at scale in Kubernetes. You've got contact information for me there, including my Twitter handle. I'll note that that's mine, not my employer's. So you'll see a bit of Tina's personal opinions on there. And I'm happy to communicate through any of those channels. I'm in my usual Saturday time. I might be riding my motorcycle or playing with my puppy or actually doing some clowning. So those are other things folks can reach out about. So as a technical director, one of my jobs, in addition to the things I do on contract, is to pay attention to what sort of things might be of interest to our customers, and then figure out what knowledge we already have within the company and how to build upon it. This talk came about because our IRAD team had been doing some work with machine learning for some proposal prototypes that we'd been working with in the past, as well as some internal company initiatives. And we were seeking some new ways to target their skills, as well as tie into some other technical competencies in the company. We're on contract, just like many of you are. And so we need to be ahead of what our customer is going to ask. In my geek reading, I had read a paper recently that talks about how to build a malware lab in the age of big data. Big data means a lot of things, but an interesting data point from the paper was that people started to consider how to deal with malware in automated analysis systems and using tools such as machine learning when there was a jump in new virus samples in the mid-1990s. That jump took us to a whole, wait for it, 4,000 new virus examples, which was then considered to be challenging to deal with using just human analysis power. Okay. So what you're seeing here is the jump in the virus making industry since then. Since the 90s, market opportunities have opened up for both developing, selling, and changing malware. We've jumped beyond hackers just trying to prove their chops or impact a single nation or a single target to nation states standing up their own hacking organizations. For example, the US Cybersecurity and Infrastructure Security Agency just called out Russia as the source behind the SolarWinds attack. You can't have missed that in the news recently. And then North Korea behind something called the blinding scan remote access Trojan strain that's targeted US defense companies. Full industry behind analyzing these attacks, discovering the variants in play so that people can share information about attack vectors and write new virus detection signatures and figure out new defense techniques. So based on these numbers, machine learning for cybersecurity has become a truly big business. Companies such as CrowdStrike, Darktrace, Splunk, they've all integrated AI and ML into their business models. A recent ZDNet article cited the chief information officer of Databricks, a guy named David Cook, saying, if you don't have AI or ML, you won't be a vendor anymore. This is the only way that any type of system can survive in this world. The traditional way of just knowing things is not going to work. And I know for this audience, y'all are fundamentally aware. You're using machine learning in a number of contexts. This talk will then work through how we can apply it specifically in the context of malware. So how does ClearEdge fit in this malware world? I've mentioned we're a government contractor. We bring together software engineering, systems engineering, data science, and DevOps are core competencies of our company. In the malware world, we do then apply that informed by cybersecurity knowledge. We build systems to recognize. We build systems to help experts analyze. That's the construct. I know, and I was checking through the attendee list or the proposed attendee list for this room. There are folks in here that are doing deep research on how to use machine learning for malware. And I am eager to have conversations with folks about what that actually looks like As a sponsor of DataWorks, we wanted to come and contribute to the community discussions and highlight what our awesome IRAD team's been experimenting with. We want to talk with folks who are working with similar tools and techniques. But basically, we started with an idea that we wanted to detect malware that hadn't been previously identified by a signature hash. We'll talk about what those are in a minute. We wanted to be able to detect some malware that had been bought or reused with some tweaks that would let it slip past the available signature sets, or something new that somebody's cooked up to send our customers' way. And for us as a company, we're interested in demonstrating how an approach can be used in an operational system. That's a key driver here. So Jason mentioned that we work with our IRAD team. To give you some context here, that's a group of employees. Some of them may have previously been on as interns. Generally, they're full-time employees who work with us on agile-based development that are then led by the senior technical leadership of the company. That's Dan Hood, our CTO, Tom Coolish, our chief architect, and myself. And we're directing them on projects and areas of interest for our customers, this being one of them. To give you a sense of the other kinds of activities they've done of late, they've evaluated microservices frameworks that we cared about for a particular contract, or worked on an open source intelligence extraction prototype, or done some work with Kubernetes environments, including, of interest for this group in particular, experimentations with ML pipeline tools. And then we're in fact building out some recruiting tools for the company that are enhanced by ML. Everybody wants to get an excellent hire. We're trying to use these tools to help us do that ourselves. So I wanted to give a special shout out to the IRAD team in general for making this talk possible. And in particular, a couple of folks who really worked to help get this talk over the line. Tyler, Kashal, Grant, Lauren, and Andrew. I'm going to avoid sharing their last names to make it too easy to try to hire them away, but I'm really happy to have them here on our ClearEdge team. Okay. So to be able to use machine learning on malware, we need to be able to extract features from the malware itself that we can then train models upon. Some of this, for those of you who are working with malware, this is going to be a very introductory level talk, or a bit of the talk, but I recognize that lots of us come from different domains, and so I wanted to set a little bit of ground rule. DataWorks had sent out a read ahead kind of post for those who were interested in looking at this information. What I provided to Jason was the book Malware Data Science by Hilary Sanders and Joshua Saxe. It gave us a great way to equip our IRAD team and get them started on this path. And it is a good introduction for how to approach this type of thing in general. We'll talk in a few minutes about what we used from that and then where we took it further. No fair if we just show you what came out of the book that you could read yourself. Though seeing that in an hour is a pretty good use of your time. All right. So as one is analyzing malware and trying to get some information from it, there's basically two ways to look at this. The picture on the left is intended to represent static analysis, and we'll talk about what that is. I just happen to like the girl's picture with her hair up on end. And the picture on the right is dynamic analysis. That actual picture is of a carnival ride that really messes with you and spins you around, and all kinds of things can come out. As a sibling of mine who I was trapped in the car with one summer can say, lots of things came out at that point. Nice cleanup of the car. All right, so static analysis. The idea behind static analysis is I give you a file and you need to figure out what you can tell about it without running the file. The idea, this is malware. And we're going to talk in our demo about how we structured this to more safely deal with it. But these are potentially malware. These can do bad things to your system. Things that one can pull from taking a look at the file, there's a number of things. You can take a look at what the name of the file is, what it says it is, its extension. Now I'll actually say the next one down, what the operating system thinks it really is. It's a common practice in a CTF. You get a file, you ask the system what it really is, so you can figure out how to interrogate it. You can take a look at its size. You can take a look at how it hashes, its MD5 or SHA hash, where it's loaded on a system. If you're looking at it on a system itself, is the file obfuscated in some way that can provide some tracers? If you look at program header metadata, strings within it, you can even actually extract images from the file, and those can lead to some info. I gave a version of this talk a couple of months ago, the intro bits of this talk anyway, at the UMBC Cyber Practicum, and had pulled out some files. All of the hacker movies that have you show interesting images in malware, those are the kinds of things you're looking for. So lots of malware detection systems use some of these aspects, right? MD5 or SHA hashes are often used. That lets you basically calculate a hash on the file that uniquely identifies, for assuming you've got a large enough hash space, and these generally do, that this file has these contents, and if you can identify that is a malware set, then you no longer, whenever you see it again, you can say, all right, this file hashes to that SHA or MD5, I see that file again, I can treat it as such. A similar usual technique is then to look against known lists of viruses, and there are multiple lists available out in the ether. Virusshare.com hashes is one, for example. I used this approach for CTF not too long ago. They gave me an image of a system and asked which file was the malware, wrote a script which traversed the directories, calculated the hash of each file, looked up the hash against the bad file list. It's not a great solution for hunting malware at scale, but it was workable enough for that capture the flag. Okay, there's a weakness to this though. And remember, we spoke earlier about there being this market out there for viruses to be resold. Often when they're resold, they're slightly changed. If they're slightly changed, their hash will change. So if you taking a look at this example here, the two files, they're off by the single last couple of digits in the hex dump. You get completely different SHAs associated with those files at that point. There are more sophisticated techniques for examining hashes, and there's a link here to a great article to look at those. But then there's also, if you're researching this based on lists out made publicly available, some of those will roll over, right? And that list group hasn't seen that hash in a while, and so it drops it off its list. You then are tied to whatever their strategy is for rollover. To get the strings from a file, that was one of the bits of static analysis. You can find the printable strings in an object or other binary file by actually running the strings command on it. And that'll give you all of the strings in that file, anything that it needed to print out in any form or fashion. If it's going to provide data back to a user, if it's going to go out and interact with some other website, those constants, those will get pulled back as your strings. So what is a common check is to see if there are URLs in there that are correlated with known sites of malware, for example. Oh, my geek notes to myself. There, I'm giving you a small set. There can actually be a whole lot of data here. There's a FireEye blog post that talks about how to rank strings output for speedier malware analysis. That we did not include that particular data in this set or in our approach, but is something that could be used forward. All right, so that's strings. Strings are a kind of feature that you can get in your set. And the last thing that I want to show you here are signatures. Signatures are how one basically deals with, usually, a static analysis approach, doing things like looking for that VeriSign URL you saw in the string set or the serial ID that was in that string set, and setting up a condition to throw an alert. If you're familiar with YARA, which is called the pattern matching Swiss knife for malware researchers, or snort rules, or suricata rules, that last one we'll talk to a bit more as part of our demo. There are these repositories of these rules where folks have said, here are signatures that match what they've seen in malware. Many are available in repositories for use. You can import them into things like intrusion detection systems and intrusion prevention systems. So that makes for nice ease of use, ease of sharing information. It also handily makes it easy for somebody else to, here's the malware that I want to make available. How do I get past that rule that would have otherwise triggered it? Basically, that same ease of use also makes it easier to then change the attack to avoid detection. All right, so that was static analysis. Again, we'd end up using signatures on data extracted from static analysis. Intrusion detection systems will often then do that on the fly. They'll look at the metadata associated with a file. They'll look at the strings associated with a file. They'll compare that across signatures and then throw alerts that can then you can use in your intrusion detection or intrusion prevention system to alert somebody that something's going on or prevent some sort of capability. So those are a set of features that we can use in machine learning as well. And in fact, you're going to see that in our demo and talk. Dynamic analysis we'll touch on briefly. That instead of taking a look at what malware looks like in file form, you actually run it. Malware data science, I love this quote. This is like introducing a dangerous bacterial strain into a sealed environment to see its effects on other cells. You want to do this carefully because malware will do things like modify the file system, modify the registry, load device drivers, go out across the network. You've triggered all of these things. One way to execute a dynamic analysis is to stand it up in a constrained system. Cuckoo's an open source dynamic malware analysis system whose point is to help manage standing up virtual environments from appropriate templates, whatever you think is appropriate to mimic your environment, to then hopefully run the suspected malware safely and observe its characteristics. It basically records what's going on and provides a way to get the metadata from those runs, which we could then use to feed in as data for our machine learning models. I mentioned Cuckoo and dynamic analysis here to help provide ideas for more things you can do with machine learning and the pieces we've put together for this talk. That said, for purposes of today, this is just sort of a, hey, this is a cool thing we could work with. We've stood up Cuckoo for other talks. We didn't happen to do it for this one. All right, so this being DataWorks, all of that context is here to set up, well, what can we then do with that sort of data, the data extracted from static analysis or dynamic analysis? How do we then apply those in machine learning models? We opted to, and again, we're working with this from an IRAD perspective, getting an understanding of how to fit these together into an operational system. Okay, we've taken the static analysis path for the purposes of this demo, that we've taken it in two different ways. In one way, we've taken the strings extracted from the executable, and we're then using a feature hasher to map them into features that our models can use, and we'll see that in a bit. In the other, we're actually looking at the executable bytecode and doing a locality sensitive hash to then let us determine similarity across samples. Does this file that we're looking at appear similar in its structure and how it goes about doing things as malware samples or benign samples? For our data set, we're not doing anything massive in terms of from a data science context. We're using a 21,000, we needed live viruses and we needed benign executables, and we needed things that were already known to be those. We weren't, for the purposes of this, attempting to ourselves self-classify. So we took live viruses from VirusShare. There's a downloadable 21,000 sample set. And we took benign executables that were extracted from Windows. And there's a mix of 32 and 64-bit, Windows 7, 8.1, 10. As we worked with our data sets, we worry about validating them via a training and testing split. Okay. We then took and said, all right, for our feature hasher approach, we worked with Scikit Learn, which is an open source toolkit. We applied it to the string data extracted via the feature hasher. On the right side, you then see we also used a TensorFlow convolutional neural network classifier, paying attention to the locality sensitive hashing approach. For us, again, the intent here was, what can we learn about how these different approaches work and how we could stitch them together into an operational system. I am well aware there are folks here in the room who've done this and more. For us, the construct again is, what does this practically look like as we work to apply it, and what can we learn and iterate upon? So the Scikit Learn approach, and again, that one actually started with the machine learning detector examples in that book I referenced earlier. They're examples to give you a starting point, use an older version of Scikit-learn, an older version of Python, all of that we updated and worked with. And of course, they didn't do the work of integrating it into an end-to-end system. They also started with a different set of classifiers for Scikit-learn, and we decided we wanted to take that further. They used a random forest classifier. We thought and then demonstrated we could get better results using the approaches you're seeing here. We ended up using what's called a voting classifier. What that does is aggregates the data received from multiple models and says, effectively, do these things agree on what the result is? Is this malware or is this a benign data? And each of those classifiers could return a different example. There are two approaches to voting classifiers, and we'll show you the differences of what we got related to those, soft and hard. We ended up ultimately going with a soft classifier. And then the three different model or algorithms that you see underneath, we're using the support vector machine, specifically the linear one. That's a supervised training model, and it's going to define the best possible plane fit between our two categories, right? So we've got our training sets. Benign malware, where does that plane exist? What does that suggest in terms of what new samples look like? We used a multi-layer perceptron, MLP, classifier. That's a supervised learning neural network. We usually think of TensorFlow for neural networks, and you're going to see us talk to that in a minute as well, more so than Scikit, as Scikit's documentation states up front that they don't provide GPU support. Well, the boxes we were running on in the lab, we didn't wire up with GPU support, so that was either or for us. But they point to things like Keras or Scorch, where you can use Scorch as a Scikit-learn compatible neural network library that wraps PyTorch. The last one listed there, AdaBoost, is a boosting algorithm which focuses on sequencing predictors so that subsequent predictors, right, multiple layers here, focus on the samples that the predictor before it got wrong. So get the first set, decide what you got right, and wrong. For the second set, figure out how to make the wrongs closer to right and iterate until you get this aggregate model that does a good job. Context here, we ended up choosing those top three performers out of the larger set of sklearn classifiers. Scikit provides a classifier comparison page where you can, where they give you code against their own data set. We then applied it against our data set to figure out the right combination of classifiers for the thing we were using. If we just took their top three against their test data, it wouldn't have been practical and useful against our data, but you can take that approach. Here's their code, fit in your data, let it run the numbers across that and choose your appropriate classifiers in that form and fashion. So what that gave us, three different approaches for Scikit in terms of their classifiers, aggregate them in a voting classifier. The graph at the bottom, we mentioned the strings were hashed back to 20,000 features. We did do sort of a correlation. We did a correlation matrix against a subset of that data to try and get a sense, making sure that the features weren't showing us evidence of correlation across. And that's what that matrix is demonstrating. We were not seeing a significant correlation across the sample of the features that we pulled. Again, it's a subset of it, but you would have expected to see some jumpiness in our matrix. Okay, so the TensorFlow CNN. One of our IRAD team is working on his PhD focused on machine learning and cyber data. He thought we should try an alternate approach instead of paying attention to it as strings, particularly in the way that the malware data science book had suggested, transforming basically the files into images and then investigating what a CNN implementation provided for TensorFlow could then accomplish. For us, again, the key part was experimenting with approaches and then demonstrating how we could bring multiple together in a system solution. So what you're seeing here for the TensorFlow implementation, we're using TensorFlow 2.4. What we then do, we use the Simhash algorithm and actually an implementation of it. It's Leon G, I don't know how else to state that. His 2.0 implementation of Simhash in Python. That Simhash converts the file into a bit array, basically, based on its file structure, what things are near each other in the file. Similar files should have similar arrays. We convert the arrays into images using the Python imaging library, and then finally let Keras take in the image as data for TensorFlow to work with it in the CNN. All right, so let's show these two distinctly different approaches: strings, feature hashing, convert bytes into locality sensitive hashes, and then images based on those. We get different results. And we'll talk to what we saw, what that implies, and things we could do to iterate upon that further. Okay, so what you're seeing here is the raw data that we get out of the voting classifiers. We had it give us the accuracy, precision, and recall for each of the models individually, and then we took actually two approaches, and we'll show that the first is a hard voting classifier. Hard voting basically says, for our three set, whichever, if two of the three agree it's one thing, it's that thing. So if two of the three agree that it is benign, it's benign. If two of the three agree that it's malware, it's malware. It's hard, each one, hard vote. What we end up seeing is that the overall accuracy, precision, and recall when we apply the hard voting classifier is higher than any individual. We ended up, we believe, reducing false negatives. We had fewer malware samples identified as benign. In hard voting across our three, what you see on the right is just as the output of what the classifier showed for a single sample. So in hard voting, all of the models indicated that the sample was likely malware. If of the three, only one had suggested it was benign, the classifier would have still said it was malware. More classifiers indicated malware than benign. If two of the three had indicated benign, the sample would have indicated benign regardless of how close the decisions were or not. Using soft voting, we'll see that in a moment, a different result, which is based on probabilities, not just classifiers. We would have had the same outcome for this example. For other samples, the decision might have been different. Now, that accuracy rate, we were congratulating ourselves for the hard voting, for the voting classifier of 97%. That sounds great, and really sounds great compared to some numbers we're going to show you in a minute. To give context, though, a 97% accuracy rate over our roughly 4,200 test malware set gives us about 125 bits of malware that would have been missed at this accuracy level. For those of you who are wondering how we got these numbers, we use the 5-fold cross-validation, which is the default for the K-fold library, that splits our training and test data up in different sets, 5, so that we make sure that our model isn't driven by a particular test train split. And the idea here is that it prevents overfitting of the models to the data. Okay, what you're seeing here are confusion matrices for each of the individual models, and then a roll up. And here I'll call out, this is now taking it, we went from a hard voting, which says 2 of the 3 wins, to a soft voting that basically says, I'm going to compare the confidence levels for the different aspects and aggregate those to decide whether or not something is malware or benign. So a confusion matrix basically says something was, we know it to be malware and we predicted it to be malware. That's good. We know it to be malware and we predicted it to be benign. That's not so good. And you see those correlations across the 3 individual classifiers. All of these counts were actually, we mentioned the 5-fold cross-validation. To get the numbers, this is summed over that full total run. Okay, so we get similar accuracy, precision, and recall numbers on the soft voting classifier. You can, in our case, we call out, we used an equal weight for each of the models. We didn't have a reason to believe one model would give us would have a better shot of identifying. So we used an equal weight across the 3. You can change that up. We could have adjusted it based on other information or insights. All right, so now let's take a look at what we get on the TensorFlow side. And I see the question about converting the malware to an image. This is where you'll actually see the images that this creates. We use an 80-20 train test split, so this isn't the same 5-fold cross-validation. We use the images, Simhash creates an array. We use the Python image library to literally create images. These are 8x8 PNGs. We had this significant challenge. We think we can get better. You see our accuracy, precision, and recall numbers. We think we can get better numbers if we can increase the hash space, but we were running into some technical difficulties doing so. What the 2 things that we needed a fixed length hash generated for each file and a reasonably large bit space. We could get the fixed length, but we could only get it up to 64 bits, or we could get longer hash sizes, but not consistent ones, which made for challenges when we were trying to process them in a CNN. So the 64-bit hash space images are ones like you see here. I think of them like cow print, basically. But TensorFlow's CNN approach is then able to then classify the images, classify the files based on those images. Like I said, we'd like to get to a larger, something more like a 64 by 64-bit image and see how those numbers adjust. We could, our combinations of various Simhash algorithms just didn't get us where we needed to, though. Interestingly to us, though, the Scikit classifiers gave us much better results, very practically, compared to the work we were putting in with the TensorFlow on this particular path. We had 2 different IRAD groups working these things. Our PhD student was working the TensorFlow side. We had another data science student and an intern working on the voting classifier side. And the data science intern and engineer got, in this case, better results. Before I let them brag on each other too much, we understand that reality is that the Scikit classifiers are excellent, and just for the purposes of what we did, gave us recognizably better results. Okay. So other things we'd like to try, just on the ML side of things. There's another, so Simhash is actually patented by Google as an algorithm. We're using the open source implementation by Lianji, or however you pronounce his handle. Minhash takes a different approach for determining whether documents are similar, using a concept called resemblance similarity. It's understood to be more efficient in some cases, including with binary data, and also has that advantage of not being patented. And from a competencies of ClearEdge perspective, it's an algorithm that can work naturally in distributed frameworks like Spark or Hadoop. Hey, ClearEdge knows how to do those sort of things. We'd also be interested in training it over different features, the Windows program executable header, the addresses that it imports, any of the different things that you saw in that static analysis set would be possible sets. We were, again, trying to see how do we fit something together end to end that gives us something to work with. And because this is a machine learning meetup, wanted to highlight that first. I'm going to get to the showing it end to end in this next bit. We think we could create a custom hasher that retains the original strings and does things in a different way, or we could we want to experiment with the trade-offs between time and accuracy for what the space size is for the feature hasher. We chose 20,000. I think that was suggested to us out of the malware data science book. There's some things that we could work with there. And then again, we'd like to work with dynamic analysis. And I see Nick's question. Yes, dynamic analysis is computationally very expensive. So that flow, that operational flow would work differently, we think. And so we definitely picked the simpler path to work an end-to-end at first, prove out how the things can come together, and then work to see what the constraints on the system are. There are some things we could do to actually classify the malware family that would be interesting. And of course, we can use other data sets and experiment. This was a Windows data set. What about other data sets? What could this look like? Okay, so operational vision. I've shown you what we got to on the machine learning side, what sorts of things we put into the models, how those came together. Now let me give you an understanding of what I was driving the team to from an operational vision perspective. We wanted open source components. We wanted intrusion detection rather than prevention. There are a number of reasons for that, including just working through the wickets of how do we not impact end users, let analysts figure out what's going on, but not prevent somebody actually getting their job done. From an architecture perspective, we wanted to be able to support more model possibilities and some ways to scale the architecture. And then we wanted to be able to reuse or build visualizations and workflows for analysts. Again, this speaks to our strengths as a company and the kinds of things we can do for our customers. So of course, these are the kinds of things one drives one's IRAD team to do. We looked at a couple of different paths to do this. Open source offerings, Snort, Suricata, most folks know it as Bro, it's now named Zeek, various intrusion detection systems. Prior art, there was an OpNIDS product that wrapped Suricata with machine learning that seems to have disappeared off the radar. Dragonfly machine learning engine also did the same thing. Their GitHub repo says it's deprecated to be replaced by Dragonfly 2. That was supposed to be released after FlowCon 2020 last summer. Their GitHub page still says that. FlowCon 2021 was this past week, and still, as of earlier this week anyway, no release. I think that one's dead. The advantages of Suricata that these guys took advantage of and that we thought were useful, it has this ability to integrate with Lua to let us do some more sophisticated queries. It's multi-threaded. Now Snort 3 also is supposed to have that. And it's easy to use in either an intrusion detection or an intrusion prevention system. Great documentation and also an open source community. I made a mild gripe on Twitter about how one of their APIs was named, and I immediately got a response. This was slightly embarrassing. That's not how you want to put in a bug request. And they put in a bug request and are working that through. So attentive community, which is always nice. We opted to go with Suricata and then, in fact, use Saxe, which is an open source Suricata-based stack, basically, provided by Stamus Networks. Completely Debian-based. It wraps up a number of tools: Suricata, Elasticsearch, Logstash, Kibana. I believe this is, I've been pronouncing it Sirius. Somebody can correct me at some time, but they're for their UIs for management and hunting. And then they're integrating Ethbox and Alert and Moloch, which is now actually called Archemy, which is a large-scale package capture and search tool. Also, easy setup, comprehensive documentation, and a number of other things that we found valuable. Okay, so demo context. Let me move this over. Let's see. Come on. Confirming. Folks can now see something that has Saxe user up on the window. Because this is all being done in a VM, it occasionally gets confused about caps lock. So, okay. Let's start. What you're seeing is actually the front door with Sirius. This is their community edition. They've got products that are built out on top of that, but the community edition's available under GPL v3. That's interesting to us because the things that we're going to be doing here to extend it are based as what you'd consider natural extension points and plugins, and they would not be considered part of Sirius's code, which would mean we'd be able to use it in other contexts. Now, they also show you the components within it. Scrolling down, the CE application, and then the information about the Saxe distribution. All right, that last block that you saw on the right, the mouse is not playing nicely. They do provide a security platform. I'm using their stuff, so I don't mind pointing out. They provide products. I'm giving no context on whether those are good or bad. We haven't used them, but those are there if folks want to play around. Meaning there's a link to their material. Those are not the tools that are available as part of the kit. Okay. Coming back up. So we're going to start here in threat hunting. They've got several applications. This is where an analyst can look at information coming through the Saxe stack. I'll turn off my previous filters, let this come back up and through, and hit their dashboard. What you're seeing is what would be comprised of a proposed attack in progress. This is actually data being generated by us. We've got some, and I'll show you that layout of the full infrastructure on a slide in a moment, but we've got some virtual machines that are pulling random files across a repository that includes benign and malware sets. All right. So I'm going to narrow in on what this sklearn signature is showing me. Scrolling down, I can start to see data about what the source IP is. This is actually the box from which we're pulling the malware files. And then these are the boxes that are doing that pulling. And again, we're running a Python script on each of those IPs that is randomly pulling files across from this source IP. All right. So let's take a look at this in signatures. Look. I happen to know that the signature was created relatively recently, so it makes it easy to find. If we were writing the UI, this might be a little bit differently. We could probably improve upon some things here. But the point of this talk isn't so much the user experience, so much as how we can use ML to enable this interaction. All right. We can see here's my plus here. We can see the alerts that have happened over the period of time, and then can dive into the signature itself. What you're seeing here is the suricata rule that we've got worked in the background here. A couple of pieces to call out. And this is it saying anything to anything in my home network. This message is what we're going to decide this alert shows up as if it triggers. For any data to the client that has a file where that file extension is an exe, then, and the rule signature is different than anything else you're going to see in suricata or rule language. This isn't a condition of the file or the flow itself. It is really hand off the decision to this Lewis script, right? That Lewis script is going to make the decision as to whether or not this should alert within the system. And as you're seeing across a number of the file, we're pulling a file every couple of seconds, and it's saying we're getting malware across that set. All right. So I'm going to take a look at the alerts that are coming across for that particular signature. What we can see here, for each of those alerts, we've got the metadata associated with it. Again, this is their UI. We can see the data for each alert presented. We can see it either in, quote, their synthetic view, which is how they think folks would like to see it. I'm not quite sure why there's an extra E there. Or you can see it in the JSON view, which is the raw data being returned by the alert. I'm going to jump down. The alert construct itself can be ingested into Elasticsearch. That's one of the capabilities that they provide, and they provide dashboards associated with it as well. So they want consistent data for their dashboards. They do give us a way, and we'll show you how we did that, to add additional metadata to it. We thought it was important from a machine learning perspective to then say, how confident are we, and which algorithm returned that information related to the alerts. That lets us do things like use the data associated with that to go back and have an analyst assess, be able to determine which model we then want to tune, and also let an analyst triage what they care about based on that information. So the particular bits of metadata we added were this confidence value, and the model that returned it. So the soft voting model, that voting classifier, returned back an alert, so this is malware, with a confidence level of 52. Given the number of alerts you were seeing coming across, an analyst might opt to make different choices based on what those bits of data are. And again, this UI doesn't take advantage of those pieces of metadata. Were we building it and knew that we had these pieces in there, we'd let analysts dive into the information differently. Okay. So the management view is another way of looking at a lot of that data. You can very practically see, I came in this morning and turned on our basic pumpers for the different files. It's been off since our team left yesterday. A 31,900 and some % trend change in the data based on those activities. This is not what you'd actually see in an operational system. This management interface, though, lets us do things like add rule sets to the system. And so when we added that rule that included the alert signature and then the Lua file itself, we're doing things to add them through here. Now, let me show you. So, let's see. This is the actual model we're triggering. No, it's not. This is the actual model we're triggering. And we're going to view that information. Very little here. We can show the actual rules associated with it, right? And we can see the rules file. This is just demonstrating how these pieces come together and what you then see. Discard that. I pulled that up. Yep. Yes, LibreOffice. Right. So that's the data you saw originally in the threat hunting interface, and we're just echoing that it is still here. Okay. Come on, give me back my chance to close this. Okay, we'll go back to the slide set. I'll show you some code here in a bit. But let's see the infrastructure that's supporting that. For us, we're using an open source visualization tool called Overt to let us stand up virtual machines. And we've done some things to set up some private networks and read-only mounts to let us deal with this data safely. What you'll see in a minute is that ML model validation is actually being served up as a, that ML model validation Lua script calls a RESTful endpoint, right, that we're serving up via Flask. We've encapsulated that in a Docker container, and then we can scale that out across our infrastructure very nicely. So seeing what that flow looks like, the rule comes across and says, I've got an HTTP payload. I interrogated across the Suricata rules. The Lua script gets fired. The Lua script itself then calls across to the REST endpoint that's served up by the Docker container. The Docker container also serves up the script that interacts with the model. This makes it really easy to independently deploy new versions of the model. We basically can swap out what the Docker container deals with. We can deploy new rules which trigger new models. Our CNN was implemented also in this path. We ran into a hiccup there where the model didn't run nicely on our virtualization framework, but that was also working through that same flow. Basically, because it's a model based on, because it's a architecture, I don't want to overuse the word model, based on RESTful endpoints and containers, doesn't rely on state between calls other than the model, the machine learning model that's built into the container. We have a lot of options. So here, let me show you what that Lua file actually looks like. Suricata supports Lua interactions. And the basic premise here is you need an init function that says what the thing needs. It needs for this script to succeed, it needs to be given the HTTP response body. And in our case, we also needed to structure the data that was going to be returned as part of the alert if it matched. You then need a match function, which basically says yes or no. Return 1, did match. Return 0, doesn't match. In our case, that decision is based on the confidence value and result we get back based on calling the ML model. And then the ML model itself, all it's doing is calling out to the RESTful endpoint and saying, give that RESTful endpoint the file, get back the data associated with it. I've simplified the code here to fit on the slide. Let me pull it up in my workspace here. Come on. You're not coming up. Come on, come back. All right, that's not happening. We'll keep moving because I'm recognizing we're running short of time. Okay. So this pattern extends to other types of intrusion detection and intrusion protection system flows beyond files. You could be looking at the network data itself and evaluating what's going on. Same kind of pattern. Here's the kind of thing I want to collect in the rule. Here's what I then want to hand off to the Lua script. We can optimize this to only test on files or flows that don't match other signatures. Suricata's got, for example, this rule signature tag that says, take a look at these MD5, this set of MD5 files, MD5 strings in a particular file name. We can basically say, if the MD5 hash for the file that we're dealing with isn't in a file name, process it through. If it is, let some set of other alerts pick this up. Suricata has added some things to deal with storing the PCAP. If there's an alert, we can use that for some further analysis. Again, whatever models we come up with aren't guaranteed to catch all things, or we want to refine what's going on. Having PCAPs to work with across the data that work through the system would be highly useful. And then you've heard me mention a few times, we would probably handle the user interface for workflow differently than the various analysts do. That would be interesting things to expand upon for an actual tool. I'm a Kubernetes geek of late anyway, so the idea of using orchestration to scale out the number of available containers to handle the model requests is also of interest to me, to be able to scale this kind of thing out. Okay. If you were interested in the kinds of things ClearEdge is doing, we are holding an upcoming virtual event. This is not a geek event at all. We do our own thing on YouTube occasionally, and we call them Tech Talks. We have our YouTube channel. This is just for fun. Come out and check out our Murder Mystery Madness event coming up on the 28th at 4 p.m. And there's contact info here for our careers team if you want to work with that. And with that, I open it up to questions. Further bits in the slide here have links to the different resources that we've included or referred to.
Thank you, Tina. So I guess like related to the slides, there was a question. Can we post these? You can let me know later, but there was some interest in seeing if we could post the slides since you had some interesting things and references and resources.
I will my expectation is yes. Let me have a conversation with folks on Monday to verify.
I assume that's fine. So there was a couple questions about some of the analysis, and I'm trying to parse some of these. One of the first questions was that some malware can kind of detect if it's running in a VM and behave differently. So like, did you have to address that? Do you have any thoughts on that?
So again, we didn't end up working that path in terms of doing the dynamic analysis. But yes, I am aware of that and have seen actually some blog posts of late reference. There's a neat group on LinkedIn of folks who are interested in cyber and malware analysis, where folks are posting, and here's how you should configure your environment to make it least likely that these various detections are going to get tripped so that your dynamic analysis can succeed. There are known techniques for attempting to refine for that. But malware writers get smarter every year. This is always a one-upsmanship kind of game. So yeah, that's why applying multiple techniques is probably the right way to go.
Yeah, I was trying to look. I saw there seems to be a very growing focus area. There seems to be a lot of interest, a lot of different conversations. This kind of leads to my next question. I was quickly looking. I saw there was like a Kaggle challenge. I was wondering if you guys have participated or if you looked at any of the challenges. And I would assume, maybe incorrectly, that some of like the cybersecurity vendors are active in the community and maybe like offer bounties and challenges. Do you have any thoughts on that? Have you looked at any of those?
I haven't, but now I'm going to go look.
Yeah, I did see a Kaggle thing. It looked like Microsoft had done a Kaggle, and the reason I was looking because I thought, and this is another question, and I think you alluded to it. I was wondering, like data sets and everything that are available. I think you mentioned a couple of things, but I saw in the Kaggle that there was like a large data set available for folks interested in this work.
That is one of the challenges our team had to decide what sorts of data we wanted to interact with, and how do you find a significant benign versus malware sample, and how do you trust what you're getting very practically. Again, we're not a malware lab.
Right.
If we were doing this on behalf of a specific customer, we would be seeking to try to see what data sets they understood. We would be recommending data sets, but also seeking to see what they had available in their particular constructs.
So there was a question about, and this is getting a little bit in an area that I'm not super familiar with, but it was talking about the benign data and how folks have found out that when they were using that benign data, what they were really validating is that Microsoft successfully compiled the executable. Are you familiar with what I'm kind of talking about?
Again, this is the challenge. How do you decide whether your benign data is a good sample? Is it just is it only that this is Microsoft set? Can you find larger samples that are things beyond just, well, here's what you can pull off of a Microsoft operating system as part of its stock set? If you then go out to open source repositories, how do you yourself validate this is benign? Some of that, there's a link in the end called for awesome malware analysis. That whole pattern of awesome whatever is really useful, where folks are sharing their info about these kinds of things.
Okay.
Right. The point of this talk was more how to stitch together these techniques.
Right. Right.
There is lots of room for folks to debate and relate to this kind of challenge. And I actually see Edward commenting.
Yeah.
We talked about that problem in one of these meetups years ago. It's a known problem.
Okay. So there was a question on YouTube, and I'm going to change the question a little and go to one of my normal questions. And so he was saying that it sounds like someone that's kind of interested in this area and has done some, a basic pulling out information about a Windows driver, right? Like the process and some things. So it's just some information. And he's trying to see like what's the next step for him if he wants to learn to do this, like how he converts that into features and things. So, and I think you already said this, but I mean, would you still say that the book is probably the best place to get started? Like if people are interested in this area, what would be the path that you're going to recommend to someone?
I am going to recommend that malware data science book. I'll also say DataWorks had a talk about a year ago, actually. Charles had given one where he walked through dealing with cyber data. I don't recall it specifically being malware, but DataWorks has, you guys have videos of folks who've come to give talks like this in the past. So I'm going to start with malware data science. I'm going to look back over your repos, and then I'm going to look at things like DEF CON videos to give me a baseline of where I can start to glean some information. I will also post that state that we've got enough experts in this meetup generally. Right. Thank you, Edward. I was going to say who approached this and might have some things to suggest.
Yeah, for those that are not sure what we're talking about, so Edward Raff is in the chat, and he's an expert in this area too. So I would recommend looking up him on Google. He's posted some stuff for those on YouTube that aren't seeing it. I can try to copy it over real quick. And then also there was a reference to Charles. So I'm trying to find that. There was a talk that we had done a couple months ago, and I thought I recorded where Charles was talking about. Yeah, I have it right here. So I'll find that and I'll post that.
Of last year. We were still meeting in person. I went to Loyola to catch his talk, and we brought our laptops to work through the different exercises.
Okay. Let me see what other questions I had. So I was actually curious. This is more my question, honestly. I was wondering, I'm assuming as you were doing this, you're kind of looking to see what's going on in industry and commercial. And I was just wondering, like, who's the leaders in this? Like, what companies are kind of pushing this? And I would assume they're doing this for commercial products, right?
Right. And you heard me drop a couple of names early. CrowdStrike, Darktrace, Splunk is more an enable. They've got kits to integrate with their things. And I recall somebody reached out to me on LinkedIn and asked if we were using some of these things already. RVector was open source specifically, practically because our customers don't tend to buy products. They're suspicious of that. We end up seeking to learn from what products are doing and then make the case to the government in terms of, here's what we can do, here's what the product can do, which path would you like to go down? And they're generally biased towards having full control of their system with an open source perspective. Now, I can shoot a resource list to you, basically pull the set out of the slides. And again, I believe I will be able to release the slides. I'm realizing I used our stock template that says it's company confidential, so I now need to go back and cross-check. I don't believe that'll be an issue.
That makes sense. So again, yeah, sorry, I had another question that kind of deviates a little from what your IRAD, but I'd just like to get your thoughts on it.
Sure.
Are we going to start I mean, it kind of alludes to what Nick was saying, how much like the how you're kind of doing the analysis offline, and then you're kind of, I guess, running it because of the resources uh, on like a computer. But are we seeing stuff for like IoT and phones and stuff? Are we going to see more sophisticated malware analysis using things like this?
So my understanding is TensorFlow models will now
Mm.
work in smaller scale devices. So
Oh, that's cool.
yes, that is exactly a possibility. I'm not personally familiar with the how sophisticated those models could be, how what the trade-offs are in using those kinds of constructs, but yes, that is in the realm of workable.
Cool. Um, Let me see. Does anyone have any other questions? I'm not seeing any other questions. I think you addressed most of the things that I've seen. And some of the questions I had, you kind of already answered. Is there anything else that you're thinking, Tina? Like, is there any falling parts? And again, I would strongly suggest that people, if you're interested in this, reach out to her, and we will try to get the resources. And there are, as Tina said, there's definitely others in the group that have done some talks and are experts, so we could probably get some introductions going. But if you have anything else, Tina, I'll let you close it out, and then we'll see everyone in February.
I just, again, the genesis for this came because our team wanted to better understand how to do things. I think there are other folks on this line who have that possibility. I would be a really poor advocate for DataWorks as a sponsor to not encourage other folks to do this kind of thing. Tackle a problem, see where you get, present it to the community.
Cool. Well, thank you everyone for joining us on a Saturday. I hope everyone stays safe and healthy and have a good weekend. And we will see everyone in February. If you do have any questions, you can always reach out to me, info@dataworks.org, or through the meetup page, and I can try to introduce you to the folks that we're talking about, and send you what I have. But we will, the video will be up and available once I clean it up. And once we get the resource list, I'll try to get that available too. So with that, thank you, Dina. Thank you very much. Really great talk. And I'll talk to everyone later.